A common assumption when you work with time series data is that the data is stationary. The basic idea behind stationary data is that it sort of looks the same if you look at a small proportion of it, no matter if you consider the data in the beginning, in the middle, or at the end. More strictly speaking, the time series is stationary in the weak sense if the expected value is constant, if the variance is constant, and if the covariance between two time periods only depends on the distance that these time periods are from each other. In this lecture, we'll have a look at the problems that may appear when you do analysis with non-stationary data. Here I have data on GDP for Sweden. This is in billions of US dollars from 1965 to 2015. And here is a plot of the GDP of Sweden. I think it's reasonable to conclude that GDP of Sweden is not stationary data. There is a clear tendency for the expected value to increase over time. But keep in mind that just the fact that we have a time series which is increasing over time is really not conclusive evidence that it's non-stationary. For example, I cannot really completely rule out that this is just a temporary cycle, such that maybe as time goes on, this perhaps turns down and then goes like a cycle like that, so that there is actually a constant expected value which is somewhere around 300. However, we just have to exclude this possibility as not being very realistic at all. A much more likely scenario is that GDP will continue to increase as time goes on. Perhaps the growth rate will slow down, perhaps it will pick up, but it's really unlikely that the GDP will come back to levels that we had in the middle of this period. So let's just agree that this is not stationary. So next I've added consumption in Sweden, and here I made a plot of both of them. GDP, blue line, orange line is consumption, and just like GDP, it's reasonable to assume that consumption is non-stationary as well. There is a clear increase in consumption over time. So in the next step, let's try to estimate a consumption function. So let's see if we can determine consumption as a function of GDP. To do that, I can do a linear regression, but since I have only one variable, I can also do a scatter plot and then just fit a trend line to this. And it's a little bit easier to see. So let's mark the data and just do a scatter plot like this. And if I add a trend line, we will get the estimated consumption function. I will also display the equation and display R square. So here it is. The marginal propensity to consume is about 46%, but the stunning result is the incredibly high R square. We are able to explain consumption using GDP, and we're able to explain 99.9% of the variation in consumption. This is almost scarily good because it kind of seems like there is nothing else that affects consumption apart from GDP. But as we will see in a second, this incredible result is partly due to the fact that we are using non-stationary data. To see that this result is very suspicious, let's try to explain the Swedish consumption using the GDP of Togo. Now, Togo, of course, is a country in Africa, and the GDP of Togo really should not have too much of an effect on the Swedish consumption. So I'm doing a scatter plot now of Swedish consumption. Well, first let's move GDP to the left of Swedish consumption so we get the same axis. Mark this, insert the scatter plot, and fit the trend line. Display equation, display R square, and we get an R square of more than 93%. So in the sense that we interpret R square, more than 93% of Swedish consumption pattern can be explained by the GDP of Togo. The marginal effect is about 66 or so. So when GDP in Togo increases by 1 billion US dollars, the Swedish consumption increases by about 66 billion. So there's clearly something strange going on. You may argue that the reason for this high R square is that GDP of different countries are highly correlated in terms of some world business cycle. So let's take this one step further and let's try to explain Swedish consumption with something that definitely has no effect at all, which is not even measured in dollars. So here I've added the population of India in millions. Let's do the same thing. Look at see if we can explain Swedish consumption by the population of India. So here I have on the x-axis is the population of India, and on the y-axis we have Swedish consumption. Let's again add a trend line, and we find the same disturbing result. Swedish consumption is to 93% explained by the population of India. When the population of India increases by 1 million, Swedish consumption increases by about 295 million US dollars. So there is clearly something going on here, something which tricks us into believing that there is a relationship between two variables where there really is no relationship at all. At least there is no causation. It's definitely the case that you cannot claim that the population of India is causing the consumption of Sweden. The culprit in this case is the non-stationarity of our data. All these time series are non-stationary and they all have an increasing trend. They all tend to increase over time. So we can see this quite clearly in this scatter plot of population versus Swedish consumption. If you look at the data right in the beginning, way down to the left and to the bottom, those are data points which are early in time. Those are points in the region 65, 67, 68. But as time goes on, consumption will increase in Sweden, but so will population in India. So as time moves on, these dots will move upwards and to the right. Even if there is no relationship between Swedish consumption and Indian population, because of the growth in both of them, the scatter plot will display a sequence of dots which slowly increases to the right and upwards. Because of this fact, when we then run a regression, fit a trend line, it looks like we have a tremendously nice fit. This is an example of a spurious regression. Spurious is a word that means something like not genuine or not authentic. So that's quite a nice name for this problem. There is no genuine relationship between Indian population and Swedish consumption. It is only a consequence of the fact that both of these variables depend on a third variable. And the third variable in this case is time. Both population and consumption depend positively on time, and that is what's causing our problem. The conclusion of this little experiment is that you should really try to avoid doing econometrics with non-stationary data. The risk is always that you will discover a really strong relationship between the variables, which is really due to nothing but the fact that they all increase or decrease over time. With stationary data, there is no such trend in the data. There is no trend towards an increase over time or a decrease over time, since the expected value for both variables will be constant. There is an important exception to this rule of not running a regression on non-stationary data, and that's when the variable are what's called co-integrated, and we will get back to that topic a little bit later. As a final exercise, let's run this regression explaining Swedish consumption with Indian population so that we can estimate these parameters and get the standard errors as well. So my y variable is in the E column, consumption Sweden. My x variable is in the D column, Indian population. I have an intercept and I want the statistics. This will of course give us the same slope and intercept as the trend line, but we also now have additional statistics. So we can actually check if this marginal effect is statistically significant, because it could be that this positive sign here on the marginal effect of Indian population on Swedish consumption is insignificant. So if I calculate the t-value for beta for B2, it's B2 divided by the standard error of B2. So the t-value is a humongous 25. So if you set up the null hypothesis, which is as follows: Indian population has no effect on Swedish consumption, which would correspond to beta 2 is equal to 0. You would reject it at any reasonable level of significance. And this is something that you should pay attention to. If you see these type of claims in econometric that an author has found a very highly statistically significant effect of a variable, make sure that the data is stationary. If the data is non-stationary, such a statement is, as we can see in this example, highly dubious.